Hey there, calculus fans. Dr. Andy Lovelace, longtime instructor at the University of Washington. Here I'd like to explain what we mean by the derivative of a vector function and how I've come to understand it and how I think about it. And this explanation, I think, will help you also understand how we think about the second derivative in some of the lectures to come. I have kind of an exotic example here. I mean, you can have very interesting things happen in 3D. We're going to watch this thing move around. And you'll notice I have the point, which we think has the point given parametrically, and have a vector pointing at it, which is the position vector. A lot of students get confused by the notation. Why are we writing it as a vector? I think this will explain that a little bit, but I'm going to stop this somewhere. And let's go take a look at what's happening. We would like to find a tangent vector. We've learned through calculus. I'm assuming people watching this video have seen a little bit of calculus. Even if you haven't, you'll get some of the ideas. We would like to find a vector that's tangent, that points the direction we're going. That turns out to be extremely valuable for lots of things. You've seen that in Calculus 1. It allows us to do optimization and all sorts of things. This just allows us to kind of understand the direction it's going. But how can we find such a thing? Usually the way you find a vector, or in 2D a slope, is you need 2 points. So this is a recurring theme in calculus, which is we need 2 points. We don't have 2 points. So what are we going to do? So what we do is we grab another point nearby. We say, well, here's a point. Here's another point nearby. How do we do that? Well, we say this is the vector r of t, where we are at time t. And this is the vector r of t plus h, where h is a small amount of time later. And then we connect those two. And we have a good way to connect two vectors. We subtract, which I've shown you written here. And I can show that here. Let me get rid of the tangent vector, which we're going to slowly build towards. Here's a little bit later. And I've made it so I can adjust the times. And I can adjust how much later. So here's much later. Here's much, much later. And here's just slightly later. So if you just subtract the 2 points, it gives you this vector. Can't even see it there because I'm too close. I'm going to make it a little bigger. So we call it a secant vector. And this should feel a lot like things you did in Calculus 1. Now you can't take the limit as h goes to 0. Well, you can. I shouldn't say you can't take the limit as h goes to 0. I'll show you it right now. We'll let h go to 0 and see what happens. So here I'm going to let h, that's letting h get bigger. Let's let h go to 0. You get nothing. You get just a point. I was trying to find a vector. So how do we deal with this? It turns out we think of this as displacement, if this was a physics course, and we'd like to divide by the amount of time. Now we're not actually dividing, we're rescaling in this sense. We're rescaling the vector. Now, sometimes students get confused. They're like, if you divide, don't you get shorter? Well, I always use an example like this. If you divide by 0.001, you actually are multiplying by 1,000. So as h gets less than 1, this gets bigger. So I'll show you that. Let's divide by h. Right now, the h I'm looking at is about 0.7. If I divide by h, you got a little longer. So that's what we would call like an average velocity vector. We've divided by the time. But we'd like to know what happens as h gets smaller. So then we do it again. We make h a little smaller. It gets closer to the right direction. And notice it didn't get shorter. These two things balance each other out. Well, how can we explain that? Well, if you distribute, you start to see that this is just the regular old definition of the derivative, but component-wise. So there's a little bit of why we like to think of things in terms of vectors, because we can have these vector explanations. So then we define the derivative vector to be the derivative of each component. The derivative of x, the derivative of y, the derivative of z, evaluated at whatever our time is. And that is indeed a tangent vector. Not only that, we think of it as velocity. We think of its length as the speed because we're dividing by the time that's elapsed. That's what's happening. And it's the limit as you do this. And that limit just leads to 3 limits that we already know. So there you go. That's the quick explanation of that. But I want you to see another way to think about this is what we're actually measuring. Let's go back to that first picture. We're actually measuring how much our vectors change. So I often think of it this way. I think of a derivative as a change. So if you have a vector and you have another vector, the change in those two vectors is this, the change in r. So really what we're trying to measure when we're taking the derivative of a vector function, and I'm going to erase a few things here. If you just want a way to think about it, and this will be helpful when we go to second derivatives. Sorry for the erasing here. And I'm not an expert in vector calculus. This is just 20 years of teaching this, how I've made sense of this, coming from a place where I study number theory, which is a very different area. But I have looked into this a lot. Okay, so we're going to let h go to 0. So basically we're looking at the change in r over the change in time, or h. So you could also think of it as the change in time. And I'm just giving a little longer thought of this. And that's why we call this the velocity vector. But that change we're talking about is actually the change in the way in which they point. Okay. So it's essentially measuring the change in our location divided by the change in time. So the reason I say that is one of the things that will come up in the days ahead is we'll study the second derivative. And in studying the second derivative, we'll have a bunch of things we talk about, but it might be helpful to some to think of it the same way. So the second derivative says, okay, same picture, but I'm not going to think about how the location is changing. I'm going to think about how the tangent is changing. Okay, so there's a couple little things about that. So I'm going to replay this game. We're going to restart. I'm going to get rid of a couple things here. I'd like to keep the curve, but I'll get rid of these vectors. And let's play the game again. But this time I'm just going to draw the derivative vector. There it is at that moment. And then I'm going to draw the derivative vector a little later. But I'm going to draw it as if its tail is on that same point. So I went a little forward in time, found the derivative, and then I drew it with its tail at the same place because I want to be able to compare them. Now I'm going to shrink h a little bit so we can see it. So this is going to be the derivative a moment later. A very slight moment later. Maybe to help emphasize this, I'm going to do one extra thing in my picture that I hadn't been thinking about. So here it is a moment later. That's what I meant to do. Okay, so we would like to figure out how much they change, but we really don't want to measure the change right now. We'd like to put them tail to tail first because we don't want it to be affected by how much the curve changed as well. Okay, so we would like to measure that. So you can see that there's going to be a dramatic change if you're turning a lot. There's also going to be a dramatic change if you're getting faster or slower. Okay, let me show you what I mean by that. So I'd like to measure at this moment, maybe I have a tangent vector like this, and then a moment later, maybe I have a much longer one. I'm going to take this one and bring it back over here and put it tail to tail. And then I'm going to measure how much my velocity has changed. So this will be the velocity at t. This will be the velocity at t plus h. And sometimes I have students tell me, what can you see? Well, it got longer. What does that mean? It means the velocity increased. It means you sped up. And we turned a little bit. If you just were going the same direction, it still would be pointing the same way. So what's going to happen when I connect these and measure this difference? That's going to be the difference in the velocity. So the second derivative is going to measure the change in the velocity divided by the change in time. The change in the velocity, if you're thinking in terms of vectors, is how much they're displaced. Because of that, look at how the vector points. It points inward in some sense. Why does it point inward? Because if you go forward in time, the vector is going to point towards the direction you turn. It's also going to point forward a little bit if you're going faster. Now, if we had slowed down, then the second vector would have been shorter. And this is really what's interesting about, there's several things to say about the acceleration. The acceleration is intimately tied to forces. So that's why I like to stop and talk about this, because it's going to mean a lot. So if you slow down, like if a moment later you were going slower, meaning like if you drew the vector here and it was short and you moved it back, that means the acceleration is actually going to tilt backwards. Still going to be pointing inward, but just going backwards. That'll be the change in velocity. Okay, so let me show you this. I'm going to move this vector back, touching the other one, and I can make h bigger or smaller. Smaller I make h, the closer they'll get. But I'd like to measure this displacement. Okay, so now we're going to do the displacement in this sense, the change in the velocities. Once again, we need to rescale. So we're going to do the change in velocity divided by the change in time. This is actually accelerating a lot because look at how much when I rescaled it, it changed. Not only that, it's tilted backwards a little bit, so I'm slowing down. I'm not slowing down. I am slowing down, but I'm turning a lot. That's what that measures. As h gets smaller and smaller and smaller, it's going to get closer to what the acceleration. So that's what the second derivative tells us. It represents the change. So I'm going to just get rid of that. So this is a useful visual. Now, usually we draw the second derivative back at the original point. So we're being yanked that way very hard because we're going to turn that way. Okay, that's why it points that way. So I find that very helpful when I'm thinking about this. So if you have something going around a circle, and you have this is your direction, and then a moment later this is your direction, you can think of the second derivative as pointing this way, and usually we draw it back here. I find that helpful. Okay, so let me show you this in action. We'll get rid of those displacement vectors. We'll draw the second derivative back here. And now we have these two things that measure change. We have the derivative vector that points the way we're going. Where did I put my derivative vector? There it is. And we have this so-called acceleration vector. So let's watch them. So you can see that the red vector points inwardly. That's pretty helpful, especially when you get to these weird shapes that you have something that points inward. It's going to be longer if you're changing. Sometimes I think the object is speeding up. Let's see if I can find a spot where it's speeding up. Maybe initially it was there. So when I zoom in, it looks like, the acceleration is forward a little bit. So that means in a moment, as I go forward in time, the green vector is going to get longer. I'm speeding up. And then when it drops behind it, like right there, it looks like they're perpendicular. So now it's going to switch to probably slowing down. Yeah, it's going to slow down, slow down, slow down, slow down, slow down. And then I think for a moment there, it might have been speeding up. Yeah, it's going to be speeding up, and then it's slowing down. Maybe it's now it's going to speed up a lot because they're almost pointing the same way. Speeding up. Okay. So anyways, that's what that measures. All right. Hope that was interesting. I kind of just wanted to take some time and explain displacement in this way. I hope that was interesting.